from now on, we're recording. Okay, so I haven't gotten any acknowledgement that you can see my screen and hear my voice. I just want to make sure of that. Matter of fact, let me go in here and check to make sure the volume's good. Okay, yep, it's turned up, so you should be able to hear me. Okay, if possible, if someone could just type in there and let me know that you can see the screen and hear my voice, I'll know that we're in business. Okay, good. Thank you very much. I appreciate it. All right, good. So let me get to work on this. Okay, and I kind of set something up over here already. This is from one of the practice documents. So this is a population where we've tested a diagnostic test. We took people after this test and we examined them with a gold standard test. We checked to see whether they really had the disease or didn't have the disease. But there's a lot that we can tell from this crosstab, from this contingency table. Okay, so if I look at this in the columns, everyone that's in this column has the disease. Everyone that's in this column does not have the disease, D negative, okay? And these are the totals going across in rows. These are the totals going across, going in the columns. Okay, so in this particular study, 1,000 people are included in this study. 200 of them had the disease, 800 of them didn't have the disease. When they were tested, 170 tested positive that had the disease, 30 tested negative that had the disease. Among people that didn't have the disease, 80 of them tested positive anyway, which was wrong. Of course, just like testing negative if you do have the disease is wrong. And 720 correctly tested negative. Okay, so for a total of 250 people testing positive and 750 people testing negative. Of course, these sums include people that tested incorrectly. 250 people, only 170 of them really had the disease. And 750 people testing negative, well, 30 of them didn't have the disease. Okay, so if we had to summarize here, this is true positives, right? It's correct positives. This is true negatives, right? And this is, well, let's see, it's a positive, but it's wrong. So it's a false positive. And over here, this is a negative, right? This is a negative, but it's incorrect. So it's a false negative. Okay, so one of the first questions I might ask here is I might ask you, for instance, what's the prevalence of the disease in this population? If this is a random sample of people that were tested, what's the prevalence of this in this population? Then I might ask, I'll wait for you to answer on the in the chat box there. I might ask, my second question might be, what's the sensitivity of this test? What's the specificity of this test? What's the positive predictive value of this test? And what's the negative predictive value of this test? Okay, so you guys can maybe type in their prevalence. I was hoping to see prevalence by the time I got saying that typed in there. But prevalence should be pretty straightforward, right? That the number of people that were sampled randomly was 1,000. Right, exactly. 200 of them don't have the disease, so that's 200 over 1,000. Right? Out of 1,000 people have the disease, right? So that is equal to 0.2 exactly. Okay, I have a sensitivity. Sensitivity is how good the test is at identifying people that have the disease. 200 people have the disease. It correctly predicted they had the disease in 170 cases. So the prevalence, sensitivity is 170 over 200, okay, which is equal to, I think, 0.85, if my head math is right. Okay, so how many people, what about specificity? Well, the specificity is the percentage of people that don't have the disease that correctly tested negative. Okay, so how many people don't have the disease? 800. How many people did the test correctly identify as not having the disease? 720. So the specificity is 720 over 800. Okay, somebody can figure that out for me. I'll fill it in eventually, otherwise I'll just leave it that way. Okay, now what about the positive predictive value? Whoops, I must have clicked something there. What about the positive predictive value? What does that mean? Well, that basically is a measurement where if having tested positive, in other words, you've already tested positive, what's the probability that you have the disease? So how would we describe that in probability notation? Well, you've already tested positive, but what we really want to know is the probability that you have the disease. So the probability that you have the disease given that you've tested positive. That's the positive predictive value. So in our case, the positive predictive value is how many people that have tested positive. 250 people have tested positive, but 170 of them actually have the disease. So the positive predictive value is 170 over 250. Okay, so that's going to work out 30, I think 68%. Right? Am I right about that? I'm guessing 6.68, but you can tell me if I'm wrong. Right? Double that would be 34. Double that is 6. I think I'm right. Now the negative predictive value is the probability that you don't have that you don't have the disease, given that you've tested negative. In other words, the right outcome. You don't have the disease given that you've tested negative. Okay, so now, how many people have tested negative? 800. How many people don't have the disease that have tested negative? 720 out of 800. And again, I'll leave that up to you. Again, it's same as the specificity. In this case, that's absolutely a coincidence, by the way. I'm sorry, I made a mistake there. 720. The number of people that tested negative, is 750. Right? 750 people have tested negative. 10 incorrectly, 720 correctly. So it's 720 people who tested negative and have the disease over 750, the total number of people that tested negative. Sorry about that little glitch there. Okay, so those are the things that you might come across if we ask you about to describe from a table like this what the specificity and probabilities of having disease, having prevalences, so on and so forth. Those are the kind of questions that you might come across in a test. Okay, so now there's another way we could look at this. There's another way we could look at this in which we give you the I tell you, let's see, what's the prevalence? Prevalence, I'm going to say, in this particular population is 5%. Well, what's the sensitivity of the test? Sensitivity of the test, maybe some study determined that it's 90%. What's the specificity of the test? Say that's also 90%. Now, I may ask you, what's the positive predictive value for this test? Well, we know the positive predictive value is which is the probability that you have the disease, given that you've tested positive. Okay, just putting that in there, just so we get a little bit of comfort with that notation, is equal to, well, what's it going to be equal to? It's a number of people that test positive that also have the disease, right? They've tested positive, they actually have the disease, over the total number of people that test positive. That's going to include people that tested positive that have the disease, just like the top, plus the number of people that test positive that don't have the disease. So that's where that weird formula that we were working with comes from. Now I'm gonna copy it in here because it's going to take me forever to type it in. But on the top, it's let's see, it's going to be the prevalence times the, I think, the sensitivity. Let me just go online here and get a copy of it so I can paste it in. Let's see. Oops. Let's go to images. Let's get a good version of it. Well, it usually comes up. Oh, here we go. This version. That's not what I want to do. Well, usually it comes right up. Maybe it's off my screen here. Oh, here we go. Here's a version of it here. Okay. Bayes rule. Okay, and we're going to take the most descriptive one of it. I'm going to grab this one down here. Okay, because it's going to be the easiest one to work with. Now you probably want to write that down somewhere. It's an open book test, so you can if you want, you can have notes with you. If you're online, of course, you'll have access to all of this stuff. So let's see, positive predictive value. I'll drop that on the desktop. And I think I can just paste it in. Let me, let's see. No, I'm going to have to drag it in. No, I didn't imagine that, right? I did drop it on the desktop. Maybe I dropped it into documents. No, it's not there either. There it is. Where did I put it? No, well, let me drag it in there. On the desktop now, I think. Here we go. Okay, here we go. So I'm going to drop this in here. Now I'm going to have to get to it. I'm going to be dragging this across here, I think. Let me clear up a little space here. We can see it. Now I should be able to grab it. Yep. Okay, so there's our problem. Okay, so I'm going to have to work from memory here again. So actually, I think the others are specificity and sensitivity. I said were 90%. So I can just sensitivity 0.9, specificity 0.9, 90%. Okay, so let's work this out. Okay, so the sensitivity is 0.9 times the prevalence, which is 0.05, over the sensitivity times the prevalence again. Remember, this is the proportion of the population that tested positive. 5% of the population had the disease. 90% of that 5% tested positive. In other words, that times that is 4%, right? So 4% of the population had the disease and tested positive. So that's the true positives. I'll put them down here also. Those are also true positives. Plus the number of people that didn't have the disease that tested positive. So the number of people that didn't have the disease is 1 minus the prevalence. The number of people that incorrectly tested positive that didn't have the disease is 1 minus the specificity. 90% of them were correct. Negative 10% of that population doesn't have the disease tested positive even though they didn't have it. So this is really just the false positive, plus 1 minus the specificity, which is 0.1, times 1 minus the prevalence, which was 5%, which is 0.95. Okay, so if we work that out, we're going to get the positive predictive value. Do you need me to work that out? Okay, I said, oh, good. I'm seeing you guys are working this stuff out in the background. Juliana says that the positive predictive value is equal to 0.14. Okay, that sounds interesting. Let me go back to our previous look here. Our positive predictive, I'm sorry, yeah, that wasn't the positive predictive. I guess that was the 0.14 was, see, I don't think that's going to be a positive predictive value, right? Because it should be a pretty big number. Because if I look here, my positive predict, oh, it's a different problem. Boy, I should have stuck with the same numbers, right? So we can make it predictable. Okay, let's work this out. Since we're here doing this, then we can move on. 0.9. Let me do the bottom first. Let's see. Clear. Clear. Okay, I'm going to do the bottom first. 0.9 times 0.05 is equal to 0.045, 4.5%. 0.9 times 0.045. So I'm going to put that into memory. I'm going to clear it. And 0.1 times 0.95 is equal to this. So I'm going to try and add that to memory. See if it does it. Yep, should have done it. And I'm going to clear that. And now I'm going to take 0.9 times 0.05, divide that by what I have stored in memory. And our positive predictive value is 32%. Does that sound right to me? Let me think about this. Oh, God. So we got somebody else got 32% also. So I think I'm right. So I'm gonna leave it at that. So the positive predictive value is 0.32%. Okay, you can do the negative predictive value similarly, but the chances are I won't ask you to do it from one of these formulas. Okay, so let's move on. The other thing about probability that we covered in the first session was those tables where, for instance, I might have asked you, well, let's see, 20% of women are in this group and 10% of women. I think we actually did one of those, right? It was a table about doctor's visits and pregnancy, and 67 to 30%. And what proportion were had only one visit, or what proportion, what was the probability randomly selecting somebody that went for all 4 visits or something like that. So one of those tables, we also did an example in class that involved the number of married, divorced, marital status, and population and gender. So there was kind of a table like that where most of it was just simple proportions. Maybe a slightly more complicated question would have been a conditional probability. Well, we said, given that you're divorced, what's the probability that you're male, or vice versa, right? So there might be a little twist in there like that. So, but I think we have that on previous videos also, but I think you guys have probably a pretty good idea how to do that. Okay, so let's move on to the, I got a number of questions from about the normal distribution. Okay, so before I actually do a problem involving normal distribution, let's just really quickly just review the empirical formula and the Z table. Okay, so typical normal distribution is bell-shaped. It could be narrow like this. It could be wide like this, right? But they all have something in common. And that is, number one, that they are symmetrical about the mean. I'm going to call the mean of this one 100. And the standard deviation describes their spread. They're bell-shaped, symmetrical. You can fold it over on the mean. It's the same areas. And like histograms represented the height of the bar, represented the number of people or the number of outcomes that were within the range that's on that bottom line, right? So similarly, a histogram is basically just a bar chart that's been smoothed out as a histogram that's been smoothed out as a curve, okay, mathematically smoothed out as a curve based on probability. Okay, but the middle is going to be the mean. A perfect normal distribution the median is also the same as the mean. If it's skewed, if it's skewed to the right, there's some people that have unusually high scores, then the mean would be higher than the median. If it's skewed to the left, then the mean would be lower than the median because it's pulled down. Where the median doesn't change much because it's a middle person. So one person that's a very low or very high can affect the mean a lot more than it affects the median. Okay? So one of the ways to look at this is that this line on the bottom here is a number line. So for instance, the mean is 100, and let's say that in this case the standard deviation is 10. So this number line, this might represent 110, this might represent 120, this might represent 130. Similarly, this might represent 90, this might represent 80, and this might represent 70. So if I look at this, what that means is that if I look at 110, the area of this distribution represents the percentage of people that have a value. Maybe this is a blood pressure above 110. If I put a dot here, this represents everything to the right of that represents the percentage of people, which is lower now because it's unusually high, that have a blood pressure higher than 120. Okay, let me just take a look at questions. Who shows how to get the entire column of numbers sensitivity. Oh, okay. I see that question. I'll go back to it if we have time. Okay. Again, that's a little bit. I'm not sure that'll come up on the test, but that'll make you construct it from just description. But that's kind of more of a teaching tool than I think it is something that you come across practically. But if we get time, I'll get back to it. Okay, so let's take a look at this. So now that's one way to describe this thing. Notice half, it's symmetrical. So 50% of people below the mean, 50% of people above the mean. Another way to describe this is instead of describing as the actual numbers, to describe it as the number of standard deviations below and above the mean. So this is 110 is one standard deviation above the mean. 120 is represented by 2 standard deviations and 3 standard deviations. A negative 1 standard deviation, negative 2 standard, negative 3 standard deviations. These numbers are generally called Z-scores. And you can calculate them if they're not obvious. For instance, 110 is 1 standard deviation above the mean. If it's not obvious, like for instance, you want to know what is the Z-score that represents the blood pressure of 115. Well, that's might be obvious to some of you, but it's not an even number. So the Z-score for a number that represents for 115 is equal to the value of the Z-score, value of that we're interested in, X, minus the mean over the standard deviation. So Z-score for 115 is 115 minus 100 over 10. So that's going to turn out to be plus 1.5. Similarly, if we were looking at a Z-score for, say, 82, that would be 82 minus 100 over 10, which is going to be equal to, that's going to be equal to 18 minus 18, right, because it's smaller, over 10, which is equal to minus 1.8. That's our Z-score. Now that Z-score, you can go to a table or to Excel and look up what the area that Z-score, that score represents for this particular population. So for instance, 80 being negative 1.8, we could go to an Excel or a Z-score and find the area to the left of 80, the percentage of people that have blood pressure below 80. Similarly, for 1.5, we could find it for this area that represents the whole left. So you could deduce, since this is symmetrical, you're going to be able to deduce, knowing what the area to the left here is, you're going to be able to deduce what the area here is, because it's what's left when you subtract this area from 1 or from 100%. This area from 100%. Now, if I ask you what's the area that's below here and above here, well, you know what the area is here because you calculated it. You know what the area is here because you got it by subtracting the area to the left here from 100%. So you know that, and you know that. So you know what both of these added together is. Well, if you know that, then you know if you subtract those added areas from 100%, you're left with the area in here. So you can do all sorts of calculations with these Z tables that you have in terms of the areas or the proportions of the populations that are represented. Now, we do have an easy rule to help us if we want to do quick calculations in our head, just estimates. Okay, and that is if you're one standard deviation, if you're within one standard deviation below and above the mean, then that represents 68% of the area of this distribution. Well, since it's symmetrical, we know that this area in here has to be 34%, and this area on the other side of the mean has to be 34%, leaving 16% below and 16% above. We also know that if I go 2 standard deviations out, that represents 95% of the distribution, which means that outside of this area and this area, that represents 2.5% on each side, since it has to add up to, it's symmetrical and it has to add up to 100%. Okay, so you can do a lot of stuff. One of the good things about this empirical rule that is especially handy is that when you do your calculation using the Z-scores and so on and so forth, and using this formula, that you can kind of go back and just use the empirical formula, numbers that are close to the ones that you're working with, and use it to judge whether or not you did this correctly. So the empirical rule is a handy thing for you to use anyway, even if you'd still have to go back and actually use the function. So let's actually work out a couple of problems that do this. Now, I'm not sure, did these come from the homework or this particular problem? Federal Reserve Bank. This one gave a lot of people some headaches here. In a certain community, the response time, I'm going to work with this one in this case, but these all work exactly the same way. In a certain community, the response time of an ambulance may be regarded as a random variable at a normal distribution, with a mean equal to 5.9 minutes and a standard deviation equal to 1.1 minutes. So first thing I'm going to do is I'm going to sketch that. 5.9 and 1.1. Okay, so let's draw our normal distribution. Okay, the mean response time is 5.9. Okay, this is a made-up example. Nobody's really claiming that it is really normally distributed, but who knows? Maybe it is. And the standard deviation is, what was it, 1.1? Did I get that right? Start talking and I forget. Yeah, I got it right that time. Okay, so let's see. What is the probability that an ambulance will take 7 minutes to respond to a call? Okay, so let's see. The mean is 5.9. And we're interested in what's the probability that it will take at least 7 minutes to respond to a call. So that 7 minutes is going to be over here. 7 minutes is going to be higher than 5.9. Well, let me see if I can use the empirical formula there. Well, what's a z-score for 7? Z is equal to 7 minus 5.9 over 1.1. So that's equal to 1.1 over 1.1 is equal to 1. That z-score is 1. So I know that if if one standard deviation below, one standard deviation above is 68% of the population, well, this area then should be half of what's left. 32% is left, so 16% is below one standard deviation, 16% should be above. So this should be about 16%. Well, that's only an estimate. Let's find out what it really is. In order to find out what that area above 7 is, I need to figure out, well, let's go to our Z table or Excel and find out what the area is below it and then subtract from 1. Okay, let me pull up our Z table. Oops. Okay, so let's take a look at this. So our z-score for positive, notice that it represents these areas represent the area from here to the left. Okay, so a z-score of 1.0, 1.0 would be this number right here. Had it been 1.05, it would have been 1.0012345. This represents the third digit. Had it been 1.19, I would have gone 1.10123456 all the way over here. This represents the area to the left, right? So naturally, if you have 0 as your z-score, that's the mean. So it would be right in the middle. So the area to the left would be 50% of the distribution. If you had a negative z-score, well, then that represents an area that's going to be less than 50%. Notice the highest one here is 50%, which is just 0 again. All the others are smaller than 50%. The numbers in here represents areas to the left. These numbers in the column represent the z-score. And these are just, they're in rows of 10 because they represent the value that's the third digit for each one of these. So you could actually go over here into the middle and say, oh, well, where is the spot? What's the z-score that represents 40% of the population is below that number? Well, 40%, it'd have to be one of these two. It's in between these two. But I'm going to take this one just because it looks a little bit better. 40%. I'm going to say that represents 40%, right? So let's see, 40%. So it's the closest one, right? To 40%. 4% of the population. That represents, this means an area of 4%. So I'm looking at 4%. The z-score for that represents 4% of the population is negative 1.75. So a z-score of negative 1.75 has 4% of the population to the left of it. We're going to keep that in mind. So let's go back here and take a look at, let's see, where are we now? Okay, so our the area, what area did I say it was? I forget now. 1.0 has an area of 80.8413. Okay, so this is 0.8413, or about 84.13%. Right, I'm going to round that to 84.1, 0.841. That leaves that leaves 0.159. That's the proportion, or 15.9%, to the right, to the right of 7. So 15.9% of the time, or the probability of an ambulance arriving more than 7 minutes, is 0.159. Okay. Now, we had predicted with the empirical rule it was 16%. So now, I feel comfortable with that answer because it kind of agrees with the range of answers that I would have expected. If I had, I did let's say my z-score is 1. So I wound up with 84%, a 0.84 from the empirical rule. I'm going to go over there and write that down for my answer. I'm sorry. I look at my z-table. I incorrectly identify it. I forget to subtract from 1. Maybe looking at the empirical rule will remind you that, the answer should be something like 16%, not something like 84%. Okay, or some other errors that might save. Okay, what's the next part of this problem? If the ambulance makes 9 responses in a given night, what is the probability that the mean response time is greater than 7 minutes? Okay, this is a population distribution or sampling distribution. What is the probability of Okay, well, first of all, it's a population distribution because they use mu and sigma to represent the standard deviation and the mean. Okay, and if they make 9 responses in a given night, the probability that they're going to be more than 7 minutes is about 15.9, or about 16%. So 16% of the time they make 9 calls. So 9 times 0.16. 0.16 would be the number of calls that you would expect to be longer than 7 minutes. Okay. Okay, good, excellent. All right. So at any rate, can't always get there in 5 minutes, right? So at any rate, let me move on to the next one. It's kind of an unusual problem. I know it's kind of a curveball of a problem. So I know that it might have thrown some of you. So let me move on. Let's do another one of those before we move on to binomial distribution. Okay. Uh, which of the previous two probabilities more relevant to probably will take it. Most actually, I answered the second question first there, didn't I? The first question was, what's the probability that it will take at most 7 minutes? So in other words, 7 down, which would have been 84%. And then, of course, the question it actually asked was the second question was the one I answered first, which was the 16%. But you guys I'm sure you get the idea. Okay, let's read the next one. Heart disease was the leading cause of death in the U.S., resulting in 24% of all deaths. Suppose 10 people were randomly sampled from all those who died in 2011. What is the probability at least one of those deaths was due to heart disease? Okay, well, I'm not sure that that's so much a problem. Well, that's kind of straightforward, right? If 24% of all deaths was due to heart disease, probably at least one of those deaths was due if you were to sample 10 people, then the probability that at least one of those deaths, that's kind of a binomial distribution problem, right? So I kind of jumped ahead into that. Let's see if I got another, before we move on to that. Sample 4,000 households, estimate overall net worth of a. Nope, we got that one again. Somebody else must ask that same question. They kind of copied and pasted these. Okay, let's take a quick look at this one. Federal Reserve sampled 4,000 households to estimate net overall worth of family, excluding some outliers. They reported that's not such a good one either. That's kind of just talking about which one's more resilient, the mean or the median. Well, I'm gonna go back to our sample problems, so I can get another one of these. Okay. Sample questions. Here we go. Okay, let's try this one. Scores on a psychomotor development index or scale of infant development are approximately normally distributed with a mean of 100 and a standard deviation of 15. An infant is selected at random. Find the probability that the infant's PDI score exceeds 103. Okay, well, let's take a look at that. First of all, the standard deviation is 15. The mean is 100. And we're looking for the probability that an infant's PDI score exceeds 103. So the difference between the mean and the value we're interested in, 103, is only 3, and the standard deviation is 15. So it's not an even numbered number of standard deviations. So it's going to be tough for me to apply the empirical rule here. So I know I'm going to be forced to go to the table or to Excel. This time I'm going to use both the table and Excel. But first, before I do anything else, I'm going to sketch this, because sketching it is always going to make things a little bit clearer. Okay. So the mean PDI score was, let me pull that back up so I can see it. The mean PDI score was 100 and standard deviation was 15. 100 standard deviation is equal to 15. Okay, I'm ignoring the fact that this is a sample for now. Not really a population, it's a sample. But I'm going to treat it as if it's a population. When we come back from the test, we're going to be dealing with samples from then on, and things are going to change a little bit. Okay, so standard deviation is 15. Find the probability that a randomly selected infant has a PDI score of 103. Okay, so we know that we're looking for infants have a PDI score of 103 or higher. We're looking for this area in here. Well, right away I know that my tables, Excel, always give me, or the particular table we're using especially, always gives us the area to the left of that. So there's going to be a subtraction from 100% or 1 here, right? So the value is 103. So it's not an even number of standard deviations above. So I'll use the formula just to make sure. Minus mu over sigma. So that's equal to 103 minus 100. It's a 3 in there. 100 over 15. That's equal to 3 over 15, which is equal to 0.20. That's a positive 0.20. 103 is bigger, right? So the z-score for 103 is equal to 0.20. I think we've worked this one problem out. I'm going to change the second half of this problem a little bit. Okay, so the z-score is equal to 0.20. So I know that the area, if this were one standard deviation, this area is going to be 16%. That would have to be 115, right? But, you know, it's 103. So the area here is going to be smaller than 32%, right? So I expect this to be somewhere between 16% and 50%. It's going to be somewhere in there. It's not to the mean, but it's not 16% either. Otherwise, it would have won. It's actually closer to the mean than anything else. So it's going to be maybe 30 or 40%. So in my head, I'm using the empirical formula. It's got to set my expectations a little bit. Okay, so let's go to our table. If I can find it. Where's our table? There's our table. Let's go to our table and look up a z-score of plus 0.20. 0.20, okay, 0.200, 0.579. For our purposes, I'm going to round that off to 58% or 0.58. Okay, on the test, probably I'll ask you for that third digit, but I'll try and give you some warning about whether I'm expecting you to round it off. So this is 58% of the population is from here down. So that would leave, in other words, 0.51 minus 0.58 in this area to the right of 103, which is going to be equal to 0.42. Got what I was talking about, right? So now I got in my head that, gee, looks like I got a good answer there. Now I'm going to change the second part of the problem. Okay, in the second part of the problem, I'm going to say, okay, what's the probability that an infant will have a PDI score of, let me think about this, 32, of 68 or less? 68 or less. Okay, that's a little bit different here. So that's going to be 68 or less is going to be to the right of 68. But now I have to determine what z-score represents 68. So my z-score is equal to 68 minus 100 over 15. I'm actually going to change. I'm going to make that 69. 69 over minus 100 is 69. Okay, so that's going to be equal to 31 over 15. Okay, so let's work this out. So that 31 over 15, calculator, 31 divided by 15 is equal to negative, remember it's negative because we're to the left of the mean, negative 2.0, I'm going to round it to 7. The z-score is equal to negative 2.07. Okay, that's going to be the z-score that represents a score of 69. Let's go to our table. So the z-score is negative 2, what was it again? 2.07. 2, negative 2.07, 2.00, 2.01, 2.02, 3, 4, 5, 6, 7. The area is 0.192, right? I'm going to call it 0.0192, 0.019, I'll call it. Okay, so this area is equal to 0.0192. Okay, let's call it 1.19 for our purposes here. And I'm going to call this area up here, I think it was actually 0.421. I think it came out to. So this is point. I'm going to go to another decimal. 0.421. I think it was. Okay, but right rather than 0.42. Okay, so 1.9% of the children in this population had a PDI score of less than 69. Now, if I ask you what's the probability of having a score which is less than 69 or greater than 103, you'd add these two together, 0.429 and 0.019. Okay, you'd add them together, and that would give you 0.44. There's a 44% chance that they're either lower than 69 or higher than 103. Now, what if I asked you what's the probability that they're between 69, they're greater than 69 and less than 103? Well, that's the probability that's in the area that's left. So if 44% of the population is above or below these numbers, that means that 56% of the population is inside of these numbers, right? So 56% of the population would represent the probability of a PDI score being between 69 and 103. Now, every one of these problems is going to be different, yet every one of these problems is going to be the same. Now, I want to go to Excel for a moment. Okay. Okay, and let me blow this up so we can actually see it. Actually, I'm going to go even a little bit bigger. Okay, so there's several functions in Excel that can help us out here. Okay, and one of these functions is going to be norm sdist. Now, when I hit the open parentheses, it's going to give me some help with this function. And it's asking me for the z-score, right? You can see norm sdist, and if you have good eyes or high resolution screen, you can see that says z in there. It's waiting for the z-score. Well, I'm going to take one of these values. The z-score that I was looking for before was negative 2.07. I looked it up on the table. It represented an area of about 1.9%. I'm going to put in that z-score here, negative 2.07, and I'm going to hit enter. And it's going to give me the area, just like the table did, the area to the left of the distribution. That was norm sdist is that function. Okay, now I'm going to give you another function here, norm dist. Let's see what that is going to do for us. I'm going to say this is equal to norm dist. You can use a dot if you want to. You don't have to. Parentheses. As soon as I put the open parentheses, it's going to give me some prompting. Now this one wants x, the mean, the standard deviation, and cumulative. Now I want to remind you, it's always true with this particular function. It's always true because we're looking for areas, not a single value. So x was 69. That's the value we're interested in. The mean was 100. The standard deviation was 15, and cumulative is going to be true. Let's see what happens when I hit enter now. It gives me the area as well. So if I know the mean, if I know the z-score, I can use norm sdist. If I know the mean, you can use norm dist. Now, I think on one of the weekly sessions, I gave you a Excel spreadsheet which a bunch of these outlined along with what the arguments are. For this one, you need to know the z-score. For this one, you need to know the value you're interested in, the mean, the mu. You need to know the standard deviation. I can't do sigma here, and that's it, right? You can say true, right? But if you know those values, it's going to return that. What it's going to return is area to the left in both cases. Okay, so now what if I asked you, what, we want to, in this study, we want to find out, we're gonna send the parents of the children of the lower 10% of children that test in this PDI score. We're going to send those children. We're going to tell the parents we want you to send your children for further testing, but we only want the lowest 10%, right? So now, what PDI score represents the lowest 10%, right? So I need to find the Z-score and eventually the PDI score for the lowest 10% of children. So I know the area is 10%, but I don't know what this Z-score, this value is. Okay, so how am I going to figure that out? Well, there's a couple of ways to do that. One, with the table. I'm going to go to the table. Remember, these all represent areas. Right? So these all represent areas. So the area 10% is going to be a negative number because it's to the left. We know it's below 50%, it's going to be to the left. So I got to find the area that represents 0.1 the best. 0.1, 0.9, going up here, 0.1. Looks like it's going to be over here somewhere. Here we go. This looks like it's the closest. And that is negative 1.28. So the Z-score, negative 1.28, represents the Z-score for the lowest 10%. Negative 1.28, right? Represents the Z-score for the lowest 10%. Well, that's nice. I know what the Z-score is, but the children had PDI scores, 69, 102, so on and so forth. I need to change that Z-score into a real score, right? So I'm going to use the same formula I used before. Z is equal to X minus mu over sigma. So I know Z now is minus 1.28. I don't know what X is. That's what I want to find out, the PDI score. The mean is 100. Standard deviation is 15. So now it's just an algebraic problem, right? I'm going to multiply both sides by 15. So I got minus 1.28 times 15 is equal to X minus 100. Right? 15 on this side cancels out. Okay, so X is going to be equal to 100. I'm going to move it over to that side. Minus 1.28 times 15. In other words, 1.28 standard deviations below the mean. 100 kind of makes sense, right? So let's work that out. What does that equal to? So 1.28 times 15 is 19.2, right? I'm going to clear memory. Okay, I'm going to put that in memory. I'm going to clear it. I'm going to say 100 minus, oh no, I messed that up. 1.28. I wish they had better calculators on computers. Times 15 is equal to 19.2. I should have remembered that anyway. So first, let me clear that first, and then I'll put it in there. I'll clear this. So I'm going to take 100, and I'm going to subtract the 19.2, and it's 80.8. So if a child has a score that's lower than 80.8, he's in the lowest 10%. Okay, where is the 0.8? I missed that. Did I do something wrong here? Where's you mean on the table? 0.8? It's actually 0.08, right? Because it was the 8th column over the point. It was 1.2, and each one of these columns represents what the Z-score, the third digit. So a Z-score negative 1.20 is this number, this area. Negative 1.21 is this number, right, the 0.0. So it's just a way to summarize this table so you don't have to have, otherwise you would have to have a column 3.0, 3.01, 3.02, 3.03. You'd have to have a column that's like 100 pages long. So it's just a better way to summarize the table. Okay, so we did that using the table. Now, just so you know, you can go to Excel as well. Okay, and if I go to Excel, okay, we have a function here called norm. Actually, there's more functions even in the ones I'm showing you. I'm pretty sure I'll have to dig it out, maybe move it up to a more recent session, but I'm pretty sure that I have an Excel spreadsheet that has a summary of these functions. So let's try norm inverse. Let's see what that gives us. Norm inverse. And again, I'm going to hit parentheses. It wants the probability, the mean, and the standard deviation. Well, the probability is the probability of picking out a random individual from that population. In this case, it's going to be 10%, because we're talking about 10% of the infants, the lower 10% of the infants. The probability of grabbing one of those. 0.1 is probability in this case. The mean is 100. The standard deviation was 15. I'm going to close parentheses, see what this gives us. It gives us the same value that we calculated before, or at least pretty close. Exactly. It is the same value. Mine's just rounded off a bit. Okay, mine is rounded off to 80.8 because I was working with a table which only has 3 significant digits, okay, in the Z-score itself. Okay, so norm inverse, it wants to know the probability or the likelihood of X occurring, the mean, and the standard deviation, and it will give you the value of X, right? Okay, so it's a pretty good tool. Okay, so yeah, now again, when you look at these problems, they're all the same. Only the number, remember there was that show, you guys are probably too young. They used to be showing Dragnet, right? They used to open up with a very dramatic opening and stuff like that. And of course, it said that, like all of these things say, this is a true story. Only the names of the incidents have been changed, right? So in these problems, only the numbers and the values, the relationships, the way you use the Z-table itself, that always winds up staying the same, right? So you have to be a little bit flexible, read the problem carefully, and then sketch it. And also, maybe in the back of your head, think about that empirical formula and how the normal distribution is, how those areas relate to the normal distribution. And that'll go a long way towards keeping you from making a inadvertent mistake. Okay, so let's move on to the binomial distribution. Okay, and let me see if we got some interesting problems that are in the, while I have Excel open here, let me just quickly talk about the binom dist function in Excel. Okay, there is a function here called binom dist equals binom dist dot dist. I'll use dot dist. Same thing. See, that'll show up. If I leave it out, this same thing shows up. Okay, number S, number of successes, right? Okay, comma. This comma separates the number of trials, the probability of success, and cumulative. In this case, cumulative means something. Okay, for the binomial distribution function in Excel, a cumulative has meaning this time. Okay, so what are these various functions that I'm looking at here? Okay, so number, let's hit escape. I'm going to just get rid of that equal sign so it doesn't disappear. So a number of successes. Okay, number of trials, right? The probability and cumulative. Okay, what do all those things mean? Well, if I take a random sample of 20 people, that's a trial of 20 people. That's a sample size of 20 people. So, and the number of trials is really just the number of people in your sample. Okay, so 20 people. If I took a random sample of 3 people, number of trials would be 3. Number of successes. Well, remember, it's a binomial distribution. There's only 2 values you can have: yes or no, diabetic, not diabetic, and so on and so forth. The number of successes are the number of people out of those 20, your sample, that actually exhibit the thing that you're looking for, that are diabetic, that are over 7 feet tall, that are under 5 feet tall, who are obese, who are so on and so forth, have high blood sugars, and so on and so forth. That's the number of people out of 20. So say 3 people out of 20 happen to exhibit that symptom or that disease or that condition. The probability is the probability in the population of them. Remember, this is only what happened that one time you took that sample. But in the population itself, there's a certain percentage of people that have that condition. Let's say it's diabetes, and let's say it's 10%. So 0.1 would be the probability, right? Probability that the number of people in this population that have that disease, probability of a person in this population has the disease is 10%. Why? Because 10% of the population has the disease. Now, cumulative, you have to make a decision, right? Cumulative is whether or not you want the probability for all or just for the probability for that specific outcome. Okay, if it's for that specific outcome, if you want it for all, you say true. So then you'll have the probability that 3 or fewer, 3, 2, 1, and 0 people have diabetes. All of those combined, all those probably combined in one number. Okay, and if you say false, right? Well, false is the probability that all the outcome is exactly 3 out of 20, right? Rather than including the probability for 2, the probability for 1, the probability for so on and so forth. So I'm going to try it right here. I'm going to say equals binom dist. Again, you can use a period or not. So in this case, the number of successes is 3, comma, trials is 20, comma, the probability for the population of having that condition is 0.1, comma, and cumulative, I'm going to put in false for now. So it's going to give me the probability that I would get, if I sample 20 people in this population at random, that I would get at least at exactly 3 people that have this condition. And it's about 19%. Well, how about the probability for 3 or fewer people, including 3 or fewer? So the probability is equal to, the probability is going to be equal to, let's see, a binom dist, just like before, parentheses. Number of successes is 3. That's what happened when we took our sample, 20. 0.1 as before, except this time I'm going to say true for cumulative. And it's going to give me the probability for 3, 2, 1, or 0. I'm going to hit enter, and it's 86%. Right? So there's an 86% chance that someone, that up to 3 people, 3 people and fewer, a lot of ways to say that, right? But 3, 2, 1, or 0 are included here. If I actually went here and did it for 0, false, 1 false, 2 false, 3 false, added up all those probabilities, it would add up to 86%. Okay, just like using true here is. Okay, so now let's say I twist this a little bit and I say, what's the probability that you would get more than 3 people that have this condition? Well, I know, having done this for 3, 2, 0, and 1, that the probability of having 3 or fewer is 87% roughly. What's left? The probability that's left is the probability of getting a sample of 20 and having more than 3, 4, 5, 6, 7, 8. That's going to be equal to just 1 minus the probability for 3 or less. Okay, this can get a little tricky. For instance, if I ask you, what's the probability for getting more than 3? Right? Okay. Well, the probability for getting more than 3, well, that's 4, 5, 6, doesn't include 3, right? We've done that already. So we used binom dist 320.01 to get, and subtracted for 1 to get the probability for more than 3. What if I had rephrased that and said, what's the probability for 3 or more? What's the probability for 3 or more? Well, now 3, 4, 5, 6, they all count, right? I'm interested in probability for 3, 4, 5, 6, 7, and so on. This, I didn't include 3. Probability for more than 3 is only considers the probability for 4, 5, 6, 7. So this works for that. But now the probability for 3 or more, well, I need to exclude 2, 1, and 0. So I should be using here binom dis, parentheses, 2, comma, 20, comma, 0.1, comma, true, and then subtracting that from 1 to find the probability for 3 or more. Okay, so the real key here is when you read the problem, ask yourself, well, what numbers are outcomes that satisfy this condition? Okay, if they're asking for an exact outcome, probability of exactly 4 out of 20, well, I got to use 4, comma, 20, and so on and so forth, comma, 20.1, and false to just get that outcome. If they're asking what's the probability for more than this number, well, it doesn't include that number, right? More than this number doesn't include that number. So I got to use binom dis for that number and down and subtract it from 1. What's the probability for at least this number? Well, that includes that number, doesn't it, when you say at least? So if I say at least 3, right, that would include 3 and up. So you would first calculate for 2 and lower, right, and then subtract that from 1. Okay, so we've been going for about an hour and 45 minutes now. I think we're okay at this point. Please, if you have specific questions, post them in the discussions board. Now, nobody's answered me yet. I've posted a couple of times, but let me know for sure that if you're shy about this, you can always post anonymously, right? For some of you guys, it might be nice to post, And if you can help out, if you see another student has a question and you see it before I do, and you think you can offer some help, go ahead and offer some help. Go ahead and start an exchange on the discussions group. So number one, let me know. Somebody email me at some point, and let me know if you can post anonymously, because I just want you to. The only problem with anonymously is if anybody puts something nasty there, I got to turn that off. But I think it'll let you post anonymously. And the other thing that I would like to know is I believe it'll let you start a new thread. Now I've been occasionally creating them, like questions on assignment 1 or questions on week 2 or something like that. I've been creating areas there, but I think you can create your own thread, questions on binom dist or something like that, so other people can contribute to it. If either of those is not true, let me know and I'll see if I can adjust it. Otherwise, I'll add more categories so people can put questions in spots where it'll help. When you go to the discussions board, it'll let you know what if there are new posts that you haven't read before. So it's pretty easy to use it and to recognize when there's something new that shows up, that or when you get an answer to one of your posts. Okay, so good luck on the tests. And for a couple of people in this different courses here, people that are online, the rules for the online stuff, we discussed it a bit, but it'll be posted with the test. You'll have a period of time to do the test, but I'll make sure even before Tuesday morning, when I usually post all this stuff, that you see the rules and stuff like that. And for you guys that are brick and mortar people that show up in actual person to do this, I'll be seeing you on Monday, right? We'll sit down. You'll have the entire period to do the test. I believe that the materials that Levi and I put together for the various courses, will allow you time enough to complete it there. Now, there is the issue of SPSS exercise. I know I made you guys try something in SPSS, right? I think that for this exam, most likely, not guaranteed, but most likely, I won't ask you to actually do it during the test because I don't want to rely on, the software working well. But I'm certainly at least going to give you some tables that were produced in SPSS, similar to the ones that you produced, and ask you to interpret them. Right, so interpret a box plot or interpret an output table and so on. All right, so good luck on the test, and spend the next couple of days working on this a little bit, and I'm sure you guys will do pretty well. Okay, take care. Have a good day.